So today we are talking all about safe failures, what a safe failure rate is, how you can use it to your benefit, and why you should really know things about it. For those of you that might not yet know me, my name is Lauren Stewart. I'm a CFSE here at Exeter, and my training came from a mechanical engineering background, so oftentimes when I give examples or talk about things, I'll be in the mechanical realm. But at Exeter, I work also in that mechanical realm, helping some of our customers achieve SIL certification, helping them with things like FAMIDAs and getting their SIL cert. I also work with Exida Academy and teach some of our training courses and help people achieve their CFSE as well. A little bit about the company. I see a few of you are new and then I haven't seen you before. So if you're new to Exeter, welcome. We are involved in the complete supply chain of functional safety across many different multiple industry sectors. So whether you are an OEM designing a piece of equipment that needs things like failure rates and certification, the whole way through to the person working the plant using maintenance and proof testing and how to decommission, we have someone to help you and everyone in between, the people designing the plants, doing calculations. We have experts, we have training, we have products and tools, and people here to help make your lives easier. I like to say no matter where you are, where your customers are, where your products are coming from, we have people close by to help you out. And this isn't even the most up-to-date one. We've opened multiple offices since this. I really need to get that updated. But no matter where you guys are, we have someone close by to help with functional safety, alarm management, and cybersecurity. The last thing on Exida, and then we'll get into why you're really here today. I like to let all of my customers know this. I think this is a very important detail. Everything that we research, all of our process, our procedures, everything that we do, and excuse the pun, but we are an open book. Everything, the latest, the greatest, the most up-to-date, everything we have, we publish, whether it's in these free webinars and blogs and white papers that you can download from the website. We go to conferences and do speeches and do booths to let people know everything that's going on. We have LinkedIn, now have Instagram. We have books that have templates in it. We have our database. We get that information out there. We feel that if we have information that could make the world safer, we need to let people know that and not just hold that near and dear to our hearts. So continuously check back with us, see what we have been researching, what we're the latest and greatest, and we're always keeping that up to date. So keep checking back. And a lot of the information is free, so even if you just want to get started in functional safety, this can get your feet wet. But let's talk about really why you're here today. First of all, throughout the webinar, if you have any questions, please feel free to type them in the questions bar of the GoToWebinar panel. I am not the best at stopping and taking time for questions throughout I usually get on a roll and just keep talking away. But I will definitely take some time at the end and answer any questions that you might have and we can even flip back in the slides if need be. So let's get into what we're talking about today. We all know the most important issue of a plant is their attempts to prevent an occurrence of some sort of accident that could result in the loss of the plant, damage to the environment, or even damage to a human or even a loss of life. So a lot of time, a lot of effort, a lot of money is spent focused on finding those hidden possible dangerous failures in a safety system that could lead to those accidents. That's what normally people are focusing on in functional safety. We talk about those dangerous failure rates, especially those dangerous DUs, those undetected failure rates, those lambda DUs. However, this webinar is going to take a little different spin and a different approach on failure rates. And instead of focusing on those dangerous undetected, which we all know about, and if you don't, we have plenty of webinars and blogs to teach you about it. But there's also other important things, such that like the plant doesn't keep shutting down spuriously and just keep disrupting the process and causing time down and causing loss of money. So even though some tend to focus only on those dangerous, or especially those dangerous undetected failure rates, I don't want you to forget about those safe failure rates. So this webinar is, like I said, taking a spin. We're going to look at the safe failure rates, that spurious trip rate, see how important it is, and how instead of just pretending we don't care about those numbers or we don't need those numbers, we can do some calculations with them, and we'll see how important that safe failure rate is in this webinar. We'll also talk about the two different routes of product certification, Route 1H and Route 2H, and how those both play a part in those safe failure rates. So let's go ahead and get started. We're going to break it apart and start with looking at what exactly a failure rate is, the pros and cons of those safe failures, and then once we know what they are, we're going to switch them around. Instead of seeing them as a negative, let's try and figure out what you can do to benefit your plant with those safe failure rates. We're also going to talk about dangerous detected failure rates and how they're kind of similar to safe failure rates, and we'll discuss why. Then, like I said, we're going to look at the two routes of device certification and how they can apply to those safe failures. So this whole webinar started with someone came up to me at a trade show the other week, and they came up to me and said, "Oh, I know you." I'm like, "You do? We don't like your work. We don't like your type of work. We don't like Exeter, all of that. We don't like you guys." So I just smiled at him and I asked, "Well, why is that?" So he vented his frustrations to me. He told me stories about how his plant is shutting down, and unfortunately shutting down often, how he's losing all of this time, this operation time, how he's losing all of this money, so on and so on. It was in his mind, it was his idea that functional safety meant losing time and money. Functional safety, companies want spurious trips to happen. In his eyes, we were the bad guys. So I let him get all of his frustrations out, and then I kept my smile on my face and I told him, well, we understand how that can be super frustrating, and we don't want any of that to happen. Here at Exeter, we don't want to shut you to have safe failures. We don't want those spurious trips to happen. We don't want to shut down your plant. We don't want you to lose money. However, we really don't want you to have dangerous failures. So we really, really don't want an explosion. We really don't want a toxic leak. We really don't want people getting hurt or worse. So instead of just focusing on those things we really don't want, those dangerous failures like many people do, there's a way we can work together and still focus on those dangerous failures, still focus on preventing those accidents as your top priority, but don't lose sight of your safe failures. Don't forget about how those can also lead to very much inconveniences, frustrations, or actually problems in your plants. They can lead to real failures if they're not dealt with. So when you look at safe failures, you can think of them, just like everything in life, there's pros and cons to safe failures. First of all, they're obviously better than a dangerous failure, especially a dangerous undetected failure. A safe failure, meaning it's just going to have a spurious strip or shut down in a safe manner instead of laying there hidden or potentially not allowing the device to do its job. The safe failures are showing that your system is working properly and that things are actually doing what they're supposed to do. And it can also help you calculate the safe failure fraction. And later on in this webinar, we'll look at what the safe failure fraction is and how to calculate it, what it means for your system, and why it's important. But it can help you figure out architecture and all of that. So there's some very good things about having safe failures and knowing what your safe failures are. However, just like everything in life, there's two sides to this story. There's some negatives on having these safe failures as well. Obviously, first of all, if you have a spurious trip, that's going to shut your process down. We don't want that to happen. We don't want your process to be taken offline. We don't want you to lose time. We don't want you to lose money. And then after all of that, you need to document it and find out why the spurious trip happened and to try and prevent it to happen again. Once again, that's going to cost you more time and that's going to cost you more money. Once again, we don't want that. So you can then take those safe failures. You can find out your safe failure rates for each device that you're using in your SIFs, and you can put that knowledge to good use. How is that? As we talked about a little bit earlier, you can figure out your safe failure fraction, but there's more. You can also use your safe failure rate by figuring out what your architecture may need to be, and such as implementing a 1 out of 2 or a 2 out of 3. You can alter your safe failure rate by changing architecture, and you can also find out your mean time to feel safe. That's going to be your, if you think of it, the opposite of your probability of failure on your demand or your PFD average. This is going to let you know when to expect or how often to expect that safe failure or that spurious trip. If you can plan for it and prepare for it, much better way of dealing with it. We see many different ways of people dealing with their safety systems, especially if they're not happy with their safety systems, especially if it has a lot of spurious trips. One example is one of my coworkers went on a plant tour, and they were looking around and noticed that a safety system was completely bypassed. Obviously, this was a huge red flag in our eyes, and we called in the plant manager and said, whoa, what's going on here? The plant manager let us know, well, it's simple. This system just kept on having spurious trips. We had too many spurious trips, so I fixed it. I bypassed the safety system. And unfortunately, this happens a lot more than anyone wants to acknowledge. Sometimes safety systems are bypassed by rewiring it. Sometimes they're bypassed by rerouting the piping and the tubing, as it was in this case. Once we've even seen it bypassed by a block of wood. Really? You put a piece of block of wood in it? I guess that's one way to make a gate valve stay open, but I'm not sure if that's the best and most efficient use of your safety system. It's kind of like nails on a chalkboard for us. But once again, if you know your safe failure rate, you can calculate things with that, like your safe mean time to fail safe. You can even, if you know how often your safety system is tripping, or if it's tripping too often, you can actually change the architecture or change the diagnostics and help improve your safe failure or those safe undetected failures. So now we know a little bit about these safe failures or the spurious trips. Oh, one second. want to go back real quick. So where do you get these safe failure rates? Forgot to mention these. So depending on what type of products you're buying, depends on where you'll find safe and dangerous failure rates. If you are buying already SIL certified product, like a SIL 3 or a SIL 2 product, say your valve, you bought it from a company, it comes with a beautiful certificate. On the back of that certificate, look for the dangerous detected, dangerous undetected, but also the safe detected and safe undetected failure rates. These failure rates on the certificate are coming from FMEDAs, or failure mode effect and diagnostic analysis. And FMEDAs occur when the certification process is going through and we look at a schematic or some sort of cutaway drawing or an exploded view along with the bill of materials. And we think of every way we can possibly break it. We look at every nut, bolt, screw, O-ring, stem, seal, everything, and apply every stress that this device could see in this application and say, okay, if this happens, are we still going to be able to perform its job safely? If not, it's a dangerous. If it's going to lead to a spurious trip, that's going to be a safe failure. And we add all of those up for the entire device. And we look to see if diagnostics could have prevented that shutdown or that dangerous accident to occur. So in the end, you have a safe detected, a safe undetected, a dangerous detected, and a dangerous undetected failure rate. So as long as a product has an FMEDA or a certification, if it went through the whole certification, it'll have that as well. So you can always get the failure rates from that, both safe and dangerous. So now we know a little bit about those safe failure rates or those spurious trips. On the other hand, what about those pesky, dangerous detected failure rate? Those are super important to know as well. But that's also where a lot more of the focus goes in functional safety. So I don't want to spend a ton of time. I just want to bring up dangerous detected failure rates are sometimes brushed to the side. The undetected ones are usually steal the show. But they are those dreaded conditions that are found before an area or before a device has an issue with, and they're found by diagnostics. But in reality, they act a lot like safe failures, although they could lead to a more dangerous condition. Your process is still shut down, you're still losing time, you're still losing money being down, you still have to document and figure out why, what happened, why it happened. You still need to try and prevent it to make sure that that's not going to happen again. So a dangerous detected failure, once again, it doesn't get talked about often, but it needs to be thought about just as much, if not even more, than those safe failures. Those dangerous detected, once again, I said they're super, super important. As annoying as they are, they're more than just kind of being annoying failures. Even though those diagnostics are letting you know something's happening, if you don't do something about it, it could lead to a dangerous condition. Those dangerous detected failure rates, they are used in not only the safe failure fraction, just as the safe failures, which we'll talk about in a couple of slides, but they're also used in the PFD average calculation, so they're even more important. That PFD calculation goes on to help you calculate architecture and even your SIL rating. So super, super important you have those numbers and you have those numbers correct. If you're doing complex modeling or complex architecture, you can do all of that modeling, those calculations. Instead of using simplified equations, you can even go as far as using Markov models. But if so, you might want to use Excellentia to do that modeling. It gets pretty complicated. So when you get your information from your certificates, from all of your devices, as I said, it's super important to have those dangerous undetected failure rates to make sure those accidents happen, but no more than that. Be educated. Also ask for the dangerous detected failures and the safe failures broken up into detected and undetected. Know how often something is going to make your plant trip. Know how often it's going to be down, how often you're going to be costing you money. Don't just be standing there like an ostrich with your head in the sand. Know about potential issues and prepare for them. And even if you know about them and prepare for them, you can even start thinking on how to prevent them. So what does the standard say? Well, the standard says that all of the hardware, all of the devices going in your safety system must be compliant to the standard by one of two ways. Either route 1H, which is the safe failure fraction, which we briefly mentioned, or route 2H, which is going to be that prior use justification. So route 1H is going to be that safe failure fraction matrix, looking at all of the safe failures in the device and also those dangerous detected and comparing them to the ratio of all of the failures. Then it has tables in the standard to help you figure out what level you need to achieve or what level you are achieving. Route 2H is more of you're highly confident in the prior use of this device. Let's look into each one of these a little bit further. So first we have route 1H. Once again, that's going to be that ratio determining what the safe or detected failures are. It's going to let you know your redundancy, your architecture, whereas route 2H, you need to have high confidence, and that's over 90% confidence in your statistics and data of the prior use of all of the components of the device and the device itself. 2H lets you get rid of safe failure fraction, but it still gives you a minimum hardware fault tolerance or your minimum redundancy by a certain set of rules. So first is route 1H, or the safe failure fraction. As you can see, this is the calculation, and you need to know both dangerous detected, dangerous undetected, safe detected, and safe undetected failure rates. Once again, you can get those from the certificates or from the FMIDAs. The safe failure fraction is going to look at what are the conditions of knowing your failure or having a spurious trip compared to what is the chance of that being a dangerous, undetected, or a possible accident-causing issue. Once you've done your calculations with your failure rates, you simply come to the chart in the standards. There's different charts for different types of systems. This is the type B system. So this is the chart for smart devices. Type A is going to be your simple mechanical devices, such as your valves or actuators or whatnot. So how you use this table is you do your safe failure fraction calculation and say you came out to, let's say we're at 75%. This lets you can read this as coming over here. If you did your PHAs, your LOPAs, your HAZOPs, and you are figured out you need a SIL 1 rating, you then don't need, this lets you know, using this chart, you have a hardware fault tolerance of 0, or you don't need any redundancy, meaning you could be a 1 out of 1 and be fine. If when you did all of your SIL calculations and you found your risk reduction needed to be higher, you needed to be a SIL 2 to open up, this lets you know you have a hardware fault tolerance of 1. What does that mean? That means you have at least one set of redundancy that you need to add in to your system. Whether you're a 1 out of 2, a 2 out of 3, whichever that may be. But what if you did your all your SIL calcs and found out you needed to be a SIL 3? You had a lot of risk to remove. This lets you know you need 2 extra sets of equipment. This says you need to be a 1 out of 3, 2 out of 4. However that you can configure that. You can even be a 6 out of 8. However you want to be, you need to have 2 extra pieces of equipment. As I said, that was the table for a type B. Type B are your smart devices, where type A is your simple mechanical, non-smart devices. The second route, or second approach, is called Route 2H. Route 2H was introduced in 2010 for basically those type A or those simple mechanical devices. What happened was those valves, those actuators, solenoids, they don't really have many safe failures. They don't have much diagnostics. They can't do any shutdowns on their own. They need help to do those. So most of the failures are dangerous on their own if you look at the device alone by itself. Because of that, type A devices were getting extremely low failure, safe failure fractions, like 50%, 30%, 0%. And they weren't able to use that safe failure fraction tables any longer. So Route 2H was introduced, saying, especially for those simple mechanical devices, those valves and actuators that have been out in the market for the last 50 years and haven't been changed. This is for you. This is showing that you have a high confidence factor in the reliability of your device. However, there are certain rules that need to be followed. 2H, you need to have a high confidence factor. And that's not just saying, oh yeah, I feel good about it. No, you need to have an over 90% quality of failure data. And that is, once again, a statistical analysis. That is going to say that you have a data quality system. It's been collected, it's been analyzed, accredited, and being used. It's not just being sitting there. You're actually using it. You're finding out why failures are happening and what's going on. It needs to be application and environmental conditions must be similar. If you have an offshore capable device, don't use the same information from the telecom industry. Just can keep it in the same realm. As you can see, that's kind of hard to get that much information on each type of device, in each application, in each environment. Exida has kind of above and beyond 2H requirements. So the standard has a lot of requirements, and then we took those and even upped it a level. For us to qualify something 2H, something needs to have documented traceable field failure studies, needs to be in field operation for at least 1 year or longer, that every single component in the FMEDA has been done per Route 2H compliance. What does that mean? So when we take apart the FMEDA and we're studying what's going on, and we see each nut, bolt, seal, stem, all of that goodness, we can then see if we have enough data on that seal, if we have enough data on that type of diaphragm, if we have enough data on that type of high pressure stem, if we have over 100 million unit operating hours per product type and component type. And if each component on the bill of materials checks out to be fine, then it will be 2H compliant. If it is 2H compliant, you can then use this chart instead. So this chart, as you can see, it's simplified. You no longer are looking at that safe failure fraction. It's just saying if you want to be a SIL 1, you don't have any hardware fault tolerance, same with SIL 2. SIL 3, we're looking at we need at least 1 minimum redundancy. And SIL 4, that's just nails on the chalkboard. I'm not even going to go there or talk about that. As you can see, that table is very, very, very similar to IEC 61511 prior use justification table. As once again, no safe failure fraction. Why is that? They're they're kind of complementary. They're kind of like sisters to each other. One is looking at it from a end user standpoint, one at looking at it from a device standpoint. However, they're both that high integrity, high data quality data collection system with enough operation hours and field history to prove so. And once again, it's not necessarily easy achieving all of the data for this 2H. We've been collecting data for almost, well, actually coming up on 20 years now, and we've kept all of that data per device, per component, per application, per environment. So we can, if you don't have enough to achieve a 2H qualification on your own, we can help you out by seeing if your products meet our 2H database qualifications. If you have something brand new, such as a new innovated seal or a new cool diaphragm that's never been used before, you can't use 2H. You'll have to use 1H approach. One thing to note, no matter what you are, route 1H or 2H, if one of your devices in your SIF is that, all of them must be. So if you have one device that needs to be 2H, because it has that super low safe failure fraction, then you need to make sure every device in your SIF is going to be 2H qualified. Same with 1H. If you're doing your 1H approach, all of your devices need to be 1H qualified. So you can compare apples to apples and have one calculation for your entire SIF. Because that SIL rating is going to qualify for your entire SIF, not per device. So I'm going to wrap things up and then take some time for questions. Thank you so much for joining us today. Hopefully you enjoyed this webinar and learned a little bit about safe failures. That safe failures, you know, they're not always your best friend. They're not things that you want. However, knowing about them is extremely useful and can be very helpful in your system. Not only do you not want safe failures, we don't want you to have safe failures either, I promise. I really don't want to hear your plants being shut down or tripped. That's not being helpful. Also, think about those dangerous detected failures. Those can affect your plant just as much as spurious trips if they're not dealt with right away. It doesn't matter if you choose route 1H or route 2H, always ask for your safe failure rate, both detected and undetected, so you can figure out what's best for you. You can change your architecture, you can change the device, you can figure out what is tripping your system so often and prevent that from happening. And then finally, please remember, no matter what you do, please don't bypass your safety systems. We don't want you to get spurious trips almost as much as you don't want to get them. If you're having issues, contact us. We can help you. We can change your architecture. We can figure something out that will solve your problems. Remember, somebody did calculations that put that safety system in there because it was deemed necessary. So don't just say, oh, it's going to be okay, and bypass the system. That's please, 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 please. Okay, that's enough begging from me. So I'm going to take some questions now. If you have any later, please feel free to email me. And once again, check out our website, our white papers, our blogs, our YouTube channels. We have so much good information out there. A lot of it is even free. And just get out there and see what we're researching, figure out what we're doing, and hopefully we can get you on the right track in functional safety. And if you really loved this, you're like, wow, functional safety is awesome, I have to get more. We have trainings. We can come to you, you can come to us. We have a bunch of new trainings for the new year coming up, but we're really excited to let you know that we also have online trainings. This is new for us. We never had that before, so if you can't get to one of our trainings or take a whole week off of work, we understand. You can do it in the privacy of your own home, on your own schedule. It's not as great because you don't have an in-person trainer, but if you can't make it to us, it might be a good alternative. Okay, the first question we had is asking about the differences between type A and type B. I believe we talked about this already, but I can just reiterate just in case. So type A is going to be your simple mechanical devices. You're going to have your valves, your actuators, your solenoid. I call them your dumb devices, things that don't have self-diagnostics, where type B is going to be your smart devices, things that can have those internal diagnostics and let you know a lot more of what's going on. They're going to be more complex systems. No problem. Actually, you guys are quiet this afternoon. Those are all the questions we have for this afternoon. Thank you so much for joining us, and check back. We'll have more webinars soon. Thank you so much. Have a great day.